Dear friends, in this class, I would like to give the information about the analysis of Truss. So, in this lecture, I will give you brief introduction about what is meant by a truss and what are the principles behind it and what are the different applications and what are the different conditions. Okay. Now, I will share the screen with all of you. So, this is a part of engineering mechanics. So, the topic we are discussing is analysis of trusses. So in this lecture, we are having the learning outcome is at the end of this lecture, the student will be able to find the forces in the truss members by method of joints and method of sections. Now in your daily life, you might have seen these type of the structures somewhere, okay? So there may be godowns and bridges. So you can see in the left-hand side, right-hand side. So very big bridges on the rivers or on the between two different points. There may be hill area, there may be river area, anywhere, wherever you want, you can construct a structure like this. Now, in this, you might have observed the structure is made up of small pieces of metal, right? So, metal in the shape of metal bars. Metal bar is a long, slender bar. Okay. Slender means it is a long when the length is very high when compared to the radius or the width. Okay. If it is the rectangular strip, then you compare with the length with the breadth, right? If it is a pipe, a long pipe, a circular pipe, right, or a square pipe, so the length is very long when compared to the cross section, right? So it is called a slender, very long. Okay. So the total bridge is called, actually we are calling the bridge means by usage, right? The total construction name is bridge, but the property or the structure is called truss. Okay. So these are the different trusses, different applications, right? Now, technically speaking, what is meant by a truss? A truss is a structure is of fixed bars. You see here, right? Slender bars, right? Joined together at their ends by frictionless pins to form a pattern of a triangle. Suppose I am taking one scale. So here I am drawing the diagram. Suppose I am taking one scale like this. Okay. At the ends, I will put two holes and I will take another scale like this. And I will take the third scale like this. Okay. So here I am joining this 1, 2, and 3 by 3 pins. Here I am taking one pin. Here I am taking another pin. Here I am taking third pin. Okay. Here the pin means pin joint. Right. So here the one means the link, or you can call member. Member 1, member 2, and member 3. Okay. Now you can see the pattern of a triangle, right? So this is the first triangle. Suppose I want to extend, then I will add fourth one, I will add fifth one, I will add sixth one. Now I will add sixth one, right? So this is a pattern I can continue for a long length. Okay. Now at this end, okay, I will show you with a different color. Color. Okay, I will take another color. Right. Suppose for the supports, I will take one more. So here I will take hinge joint or hinge support. Here at this end, I will take roller support. Okay. So the hinge support will have two reactions. One is vertical reaction. Suppose this is A, this is B. The hinge will have the vertical reaction VA, horizontal reaction HA. But the roller will have a perpendicular vertical reaction only, and it is VB. Okay. You can call it as RB or you can call it as VB. Notation can be different with the different textbooks or different approaches, right? But concept is the same, right? Now you can see, so this is called a truss. This is a truss, okay? And you remember the loads act only at the joints, not on the members. Thus, every member of a truss is identified as a two-fourths member. Here the two-fourths means in each and every member. So suppose I am taking member number 1, right? Due to the load acting at the joints. So now I am applying, suppose I am taking the top 2 joints, right? Here I will apply, on the right side you take 1000 newtons I am applying, right? So the structure is ready. Now you are applying some load from top, right? So due to this 1000 newtons, there will be some force that will be created in each member. In the member 1, member 2, member 3, 4, 5, 6, 7, right? In all the members, there will be some force induced, right? So one by one, we'll check. We'll go to the deep in analyzing the truss. And what are the different applications of the trusses? They are usually designed to transmit forces over relatively long spans. You see this? Long span, right? So river bridge, very long bridges. And common examples being bridge trusses, roof truss, transmission towers. You might have seen in our college also, the transmission towers are there. So these are the different examples: transmission towers, bridge, and Eiffel Tower, roof truss. Now we'll go to what are the different types of trusses. So based on the design, you are having different names: king post truss, scissors truss, and how roof truss, Pratt truss, sawtooth. Oh, sorry, 1 minute, 1 minute. Sawtooth truss, pink truss, Pratt truss, how bridge, N, Warren truss. I think Warren truss is looking very easy, right? Okay, now we'll go to based on the properties. Types of trusses are two types. One is perfect truss, second one is imperfect. How it is imperfect? There are two types. One is deficient, one is redundant, right? So this perfect means what is the condition, right? Perfect means whatever you are expected, if it is satisfied, it is perfect. Got the point? So whatever is expected, okay, expected is equal to actual, okay, then it is called perfect. So the actual thing when it is equal to the expected, you call it as perfect, right? Now, if it is not equal, not equal means either it may be less or it may be more, right? If it is less, you call it as a deficient truss. If it is more than required, it is called redundant, okay? So these two are called imperfect. That means either you are in less condition or you are in more condition. Now, what is expected? What is actual? What is the rule actually? So now we'll go to the actual condition. If any truss is taken, number of members is M, right? Suppose in the old, in the earlier diagram, you might have seen Okay, in one of the truss I will show you. Suppose I'm taking the king post truss. Number of members, that means suppose this is A, B, C, D, E, F, right? Now you see AB, this is member number one, BC second, CD 3, DE 4, and EF 5, and DF 6, CF 7, BF 8, and AF 9. Even though you are looking, A to E will be a long slender bar, but it is not long slender bar. Between each and every 2 points, there will be only one slender bar. Even though in the diagram it is looking like, but you should not consider AE as a single member. AF, one member, FE, another member. Okay. So between any two joints, we are having only one slender bar. Now, how many members are here? 9. So, M is equal to 9. Okay. Now, J. J means number of joints. How many joints are there? A, B, C, D, E, F. Okay. So, 1, 2, 3, 4, 5, 6. So, J is equal to 6. Now you are having the third parameter, small r. Right? R means number of reactions. Okay. How many reactions are there in your total system? Right. Now you see here, what are the different supports in this? One is the hinged support at A. Are you looking? With clarity, you see? Here at A, I am having hinge support. This is hinge. Hinge or pin, you can call. Okay. It is roller. At the hinge, I am having two reactions. One is vertical reaction. Second one is horizontal reaction. So I can call it as, one second. Yeah. So this is HA and this is VA. Now at the roller, I am having only one vertical reaction at the roller. So it is VB. Now how many reactions in your system? HA, VA, and VB. So 3. So R is equal to 3. Now I will do the calculation on the right side. Okay. Now I need to satisfy the condition M is equal to 2R minus, okay, 2J minus R. 2J minus R. Okay. So M is LHS. 2J minus R is RHS. If LHS is equal to RHS, you call it as a perfect. Okay. And there are two conditions. If not equal, what are the two conditions? LHS will be less than RHS. You call it as a deficient. Suppose LHS greater than RHS, you call it as more than required. So it is redundant. Okay. Now you can see what is the value of M here? LHS value is 9. What is the value of the RHS? 2J minus R. 2 into 6 minus R is 3. So 2 into 6, 12 minus 3, it is equal to 9. So my condition is satisfied. LHS is equal to RHS. So it is a perfect frame. Perfect frame. Okay. Right. So this is called perfect frame, and M is equal to 2J minus R is satisfied. Okay. Now, so these are all different examples. Suppose imperfect. Imperfect means either less or more. Okay. Now you can see this stress in the example. Now I will clear you. At this hinge support, I am having two reactions, HA, VA, and the roller is, okay, it is B. So I can call it as RB. Now you tell me how many members are there? Okay, I will give some names A, B, C, D, E, F. Okay, right? So how many members are there? So you look after this. I am making the spring. AE, one member. Next, CE, second member. AC, third member. Now EF, fourth member. DF, fifth member. CD, seventh member. FB, eighth member. And DB, ninth member. So next we will check it. 1, 2, 3, 4, 5, 6, 7, 8. Okay, okay. 8 members. So AE 1, EF 2, 3, 4, 5, 6, 7, 8. So 8 members are there. So I am writing M is equal to 8. Now how many joints are there? A, B, C, D, E, and F. A, B, C, D, E, F. 6. Right? So J is equal to 6. As usual, the reactions are 3. So LHS is 8. What about the RHS? 2J minus R. So 2 into 6 minus R is 3. So 12 minus 3, it is 9. Now what happened? LHS is less than RHS. So it is lacking something. So it is deficient. Deficient. Okay. So this is one type, imperfect deficient Truss. Suppose it is redundant. Redundant means more than that. Now you see in this, the reactions, suppose I am taking A, B, C, D, E, F, right? So the reactions HA and VA and the roller reaction is RE. As usual, R is equal to 3. Joints 1, 2, 3, 4, 5, 6. So J is equal to 6. Now how many members? M is equal to. So I will put another color. Uh, color. Yeah, I will take blue color. Okay. So I'm giving the members AB1, AF2, FB3, and BC4, and BD5, and FC6. Now DF7, and CD8, DE9, and CE10. Okay. Now M is equal to 10. M is equal to 10 means it is LHS. Now what is RHS? 2J minus R. 2 into J is equal to 6. R is 3. So 12 minus 3, it is 9. So LHS become more than RHS. That means whatever you are expecting, you are having more than that. In general, we are thinking whatever that is expected, if you are containing more, it is better safety, like this we are thinking, right? But it is not in your steel structures or the trusses, right? When something is more required, so it is a material waste, right? Material waste. So how many excess are there? One excess. One extra member is there. Probably it is this FC. Okay. If FC is not there, it will become perfect. Okay. Right. So this is simply the explanation of your what is perfect and what is imperfect. Now, for making the assumptions for the analysis of the truss, you are having some 5 assumptions are there. How to proceed with the analysis? So, what are the assumptions? All the members of a truss are straight and connected to each other at their ends by frictionless pins. So, we are having these are to be straight. They need to be straight only. There should not be any different shape like this. Okay. And all the loadings or the external forces on the truss are acting only at the pins. You see in the earlier diagram, the F1 is acting at B, F2 is acting at C, F3 is acting at F. So you should not apply the force in the middle of the member. You need to apply at the joints only. Okay. So this is the one condition. All the members are assumed to be weightless. Weightless. Okay. So you might have observed all are made of metal, mainly steel or iron. So why should I consider the steel or iron beams with heavy weight as weightless? Because the load, whatever you are applying on the truss, is very, very, very high than truss weight. Suppose the truss weight is 200 kg, I am applying 5,000 tons. Just compare it. Okay. So when compared to the load you are bearing, your weight is very less, right? That's why you consider weightless. Okay. And all the members of the truss external forces acting at the pins lies in the same plane. That means, suppose my beam is like this, I need to apply the load on the same plane. I should not apply in different planes or spatial applications. Okay. And static equilibrium condition is applicable for the analysis of the perfect truss. So, in our earlier discussion, in the equilibrium of the forces, we have sigma fx equal to 0, sigma fy is equal to 0, and sigma m is equal to 0. So, these two are related to the forces, and this related to moments. Okay. Thank you very much for your patient hearing. In the next class, I will explain about what are the different methods of analysis of the process. Thank you very much. If you like this video, please like, share, and subscribe. Thank you.